Good day. I'm going to discuss on quantum numbers. When we said quantum numbers are numbers that trying to identify the position of an electrons in the atom. There was a theory stated by Pauli. We call the theory Pauli exclusion principles. He said that there is no any two electrons in the atom that have the same full set of the quantum numbers. So we are now going to look at these four quantum numbers and verified the Pauli exclusion principle. So these four quantum numbers are trying to describe the electrons in terms of the following. Number one, the quantum numbers are trying to identify or to define the distance of electrons from the nucleus. So we know that generally in the structure of the atom we have what we call nucleus and shell. So these quantum numbers are trying to define the distance of the electrons from the outermost shell to the nucleus. And number B, they also trying to define the shape of the electrons, the shape of the orbitals, the orientation in space and the directions of electron spin. So we are now going to look at them one by one. So number one is the principal quantum number. The principal quantum numbers refers to the energy level of the electrons. We know that generally in the electronic configuration using shell, we have what you call shells. So that shells or that number of shells indicates the principal quantum number. We have K shell, we have M shell, we have L shell, we have N shells, and the rest. So K shell is the first shell, and the second shell is L shell, we have M shell, and we have N shell. So that number of shells indicates the principal quantum number, which is N. So the principal quantum number is used to show the energy level of the electrons. Like for example, if we have sodium has 11 atomic number. So we know that in the first shell we normally put the maximum of 2 electrons. We have in the second shell the maximum of 8 electrons, and the last shell has 1 electrons. So if I ask you to give me the principal quantum number of the 11th electron, so it means that your N is 3, because your last electrons is in the energy level of 3, which is N. So it means that the principal quantum number of 11th electron is 3. And if I ask you the principal quantum number of 4th electron in sodium atom, it means that the N is 2. Why? Because the first 2 electrons are in a K shell, which is K is normally 1, meaning that N is 1. So the N, it indicates like the number of the shells. So if N is 1, it means that you have K shell. If N is 2, it means that you have L shell. If N is 3, it means that you have M shell. So therefore, if I ask you to give me the energy level of the 4th electron, it means that it is in L shell, which is N equals to 2. So therefore, if I ask you for the 5th electron is also in second shell, so it means that your N is equal to 2. Is that following? And if I ask for the first electrons in sodium atom, it means that it is in the first shell, which is K shell. So it means that N is equal to 1. So your energy level is 1 for the first electron in sodium atom, and for the 11th electron your N is equal to 3. Okay, the next thing is actually what we call azimuthal quantum number, or in some cases we call it momentum quantum number. The momentum quantum number is trying to define the shape of the orbital, and the number, or the L, it has a formula. The formula is L equals to n minus 1. The formula for azimuthal quantum number, or in some cases we call it subsidiary quantum number. In some also other textbook you will see that they use subsidiary quantum number. So it's all the same. So it has a it has a formula which is L equals to n minus 1. L equals to n minus 1. So it means that the azimuthal quantum number or principal quantum number depend on the value of n. So if you have n is equal to 2 and you want to get the value of L, so it means that you are now going to use L is equal to n minus 1. So if your n is equal to 2, so you are now going to use the formula and said L is equal to 2 minus 1. So if you have L equals to 2 minus 1, it means that you have L equals to 1. So if your n is equal to 1, if your n is equal to 1, you can also say L is equal to n minus 1, which is your n is 1. So you now say L is equal to 1 minus 1, which is equal to 0. So whenever you have azimuthal quantum number which is L is equal to 0, it means that you have s orbital. And if your L is equal to 1, it means that you have p orbital. And if your L is equal to 2, it means that you have d orbital. And if your F is equal to 3, it means that you have f orbital. So it means that the principal quantum number give you an idea of which types of the orbitals you are dealing with. So therefore, if you have s is equal to 0, it means that if you have L equals to 0, it means that you have s. If your L equals to 1, so it means that you have p orbital. And if your d is equal to 2, you also have what we call d orbital. And for L equals to 3, you have f orbital. So you have to put this at the back of your mind. It's very, very essential. It is very, very important to identify orbitals based on the azimuthal quantum number. So sometimes a question may be asked, maybe in terms of identifying the position of the electrons. So maybe, for example, if you now use SPDF notation in writing the electronic configuration of the atom. Let's say you want to write the electronic configuration of let's say helium. So in helium we have two atomic number. The atomic number is 2. So therefore we have 1s. So 1s2. So 1s2. So it means that your maximum number of electron is 2. So someone may decide to ask you what are the two quantum numbers of the second electron in the helium atom. So what are you going to say? So first you try to identify, or you try to check the energy level. So the energy level there is 1. That is the 1s to the 1 there, that is at the coefficient of s, is your energy level, which is n. So your n is equal to 1. So since it is s orbital, so the azimuthal quantum number is equal to be 0. Since it is, you only stop at s, and you are talking about the quantum numbers of the second electron. So the second electron is still at s orbital. So therefore what you are going to do, you will now say that your n is equal to 1, your L is equal to 0, because the second electron is at the s orbitals, and your energy level, which is the last energy level there, is also 1. Like for example, if I ask you for the principal quantum numbers, that is azimuthal, and the principal quantum numbers of the 11th electrons in sodium. So what you will do, you will now write the electronic configuration of sodium using SPDF notation. That is 1s2, 2s2, 2p6, 3s1. 3s1. So if it is for the 11th electrons, it means that your n is equal to 3 because the last energy level there is 3 and the orbital still remain s orbital. So therefore it means that your azimuthal quantum number is 0 because we are talking about the quantum numbers, like the principal quantum numbers and the azimuthal quantum numbers of the 11th electron. Like for example, if you ask for the principal quantum numbers of the, let's say, 10th electron. So for the 10th electrons, the 10th electron falls under 3p6. So therefore your principal and the azimuthal quantum number, it means that since your energy level there is 2, so it means that your n is equal to 2 because your 10th electron is at 2p6. So your n is equal to 2 and your p is equal to 1 because p orbital is 1. That is whenever you have 1 azimuthal quantum number, which is L equals to 1, so it means that you have p orbital. So for the 10th electron, you have n equals to 2 because your 10th electron is as 2p6 and your azimuthal quantum number is 1 since the 10th electron is also at the p orbital. Then the next thing that we are also going to discuss is the magnetic quantum number. Magnetic quantum numbers also trying to describe the orientations of the orbitals in the space. It also has a formula. The formula for the azimuthal quantum number is equal to 2l plus 1, and it takes the integers between minus l to plus l. So like for example, the s orbital, as we set, since from the azimuthal quantum number is 0, so therefore your m is also going to be 0 since l is 0. And for the p orbital, you have your l is equal to 1. So if you want to calculate your magnetic quantum number, what you will do here, you will now take the value of l. So for the p orbital, your l is equal to 1 as described from the azimuthal quantum number. So p is equal to 1. That is, when l is equal to 1, you have p orbital. So therefore you will now substitute the value of l here. So you now have m, that is magnetic quantum number, is equal to 2l plus 1. So your l is 1. So you will now say 2 times 1, we have 2. Then 2 plus 1, we have 3. So that is why you have 3 values here. That is why we have 3 values here, which is minus 1, 0, and plus 1. So that is why when we come to p orbitals, we normally see that it has like 3 boxes. We have px, we have py, and we have pz. And each of the boxes accommodate a maximum of 2 electrons. That is why p orbitals normally accommodate the maximum of 6 electrons. So for each box, the first box contains minus 1, the middle box, which is the second box, is 0, and the last one is plus 3. So for the px is minus 1, for the py is 0, for the pz is plus 1. So that is why for this. Then when l is equal to when l is equal to 2, we have d orbital. We also substitute our value of 2 here. So when we set m1 magnetic quantum number is equal to 2l, so your l is 2 for d orbital. So we now say 2 times 2, we have 4. Then 4 plus 1, we have 5. So that is why we have 5 different values here. We have, as we said, it started from minus to plus. Minus l to plus l. Here is l is not 1 actually. So we have minus l to plus l. So that is why we have minus 2, minus 1, 0, plus 1, plus 3. Plus 2. So we have 5 different values. So that is why when we come to d orbitals, we realize that we have 5 boxes. The first box is minus 2, the second box is minus 3, the third one is 0, the fourth one is plus 1, and the last one is plus 5. Then for the f orbital, we have L equals to 3. So when L is equal to 3, we also substitute it here. We now say 2 times 3, we have 6. Then 6 plus 1, we have 7. So that is why, as we said, the value is range from minus L to plus L. We have 5 different values here: minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. So we have like 7 boxes. So each of the boxes accommodate a maximum of 2 electrons. So that is why for the f orbital it accommodates a maximum of 14 electrons. Then the next thing now that we are going to discuss is spin quantum numbers. So different this spin quantum numbers is trying to differentiate how 2 electrons behave under a magnetic field, and it can only have two possible values for the spin quantum numbers. We have plus half and minus half. So actually, remember, when you are arranging electron in a boxes, normally one is pointing clockwise and the other one is pointing the anti-clockwise. That is the one up and the one down. So when you look at the arrowhead, for the plus half is the one that is actually point upward, and for the one that is pointing downward is your minus half. So that is why they said that there is no any 2 electrons in an atom that have all the 4 sets of the quantum numbers. So therefore, at least they must have a different spin. So like for example, this is an example. They said that what are the possible quantum numbers for the outermost electron of oxygen? So what is the outermost electrons of oxygen? So we remember that oxygen has 8 atomic number. So in the first shell we have 1s2, we have 2s2, then we have 2p4. So the first one we have 1s2, we have 2, look at it, we have 1s2, we have 2s2, we have 2p4. So where do we expect to have our outermost electrons? The outermost electrons is this 2p4. So now the question is, what is our n value? So look at it. If you now look at it in the p4, the energy level is 2. So our n is going to be 2. That is why we have 2 here, because our last energy level is 2. Then the next one is, what is the L value? So remember, for the p orbital, L is equal to 1. So therefore our L here is going to be 1. Then the next thing is the electrons. So it's the electrons. So for example, now look at it. Since we are talking about the magnetic quantum numbers, so since our L is equal to 1, so we are expecting to have 3 different values, because the question said the outermost electron. The question didn't say like maybe 5th electron or like 10th electron. Are you getting my point? So therefore we are expecting to have 3 different values. Then the next thing is the spin quantum numbers. So the spin quantum numbers is also going to be plus half and minus half. So ladies and gentlemen, now for example, if you were asked in the question to give the 4 quantum numbers of the fifth electrons, what is going to be the answer? The answer is going to be, okay, I think I want you to answer this question in the comment section. Thank you.